Hello, I want to welcome you to today's class. Today we'll be looking at Ionic Equations. Let's take it off. I have a beautiful quote today. This quote is from one of the greatest men that lived on this earth, Nelson Mandela of South Africa. He said, "Do not judge me by my successes. Judge me by how many times I fell down and got back up again." This is highly inspirational. At one point or the other in life, we're going to fall down, but what matters is how much time do we get up and keep going to where we're going. And if we keep getting up at any point in time when we fell, that is actually the mark of success. Let's take it off from there. Today, we intend to address two basic learning objectives. Number one, we know how to write a balanced molecular or formula equation, the total ionic equation and the net ionic equation. And then we'll also have the skill to predict products of reactions using the solubility rules. So we're going to see what the solubility rules is all about as we move on in this lecture. Ionic equations. Of course, many reactions takes place between compounds that are dissolved in water. Most ionic compounds are actually water soluble. To some extent, they dissolve in water, and when they do that, they can easily furnish the ions in which they were made of. What do I mean by that? These ionic compounds and some polar covalent compounds like the acids will break apart in water and release their ions. A good example is what I have here. You see, if you look at this, this is sodium chloride. Sodium chloride is made up of sodium and chlorine. Of course, when water is added to it, this is a solid one. You see, the state of matter is solid. It's easily, if you put this, let's say, in a jar or in a beaker of water, it's going to dissolve completely. And in solution, what happens? You see that sodium ion and chloride ion has been released to float around inside the beaker. Now, this is an ionic compound, of course, because ionic, a metal is involved, a non-metal is involved. If you look at the second one, this is an acid. This is sulfuric acid. Of course, remember that all acid will always start with a hydrogen, and this hydrogen represents the only positive ion in this compound. Now, when you dissolve this in water too, what happens? Sulfuric acid will furnish each 2 moles of hydrogen ions, and then the sulfate ion will also be left to float in water. And this actually makes these guys really very good conductors, because most of these ions will keep floating about and we're able to conduct electricity. So we're going to start on a good note. Let's try to write the problem. One says complete and balance the following dissociation or ionization equation. Now, in the previous chapters, I will also use the word hydration, how water hydrates this, but when we talked about the ion dipole interaction, that's exactly what is happening here. So now let's complete these reactions. If you look at this, potassium and phosphate is a polyatomic anion and is a single entity. So the first thing we need to do, another thing that will help here is that you need to know the charges of the various ions. And you can only know that by knowing the groups in which these metals belong. Now, potassium belongs in group 1, so it's going to have a charge of +1. On the other hand, phosphate is a polyatomic anion, and it usually have a charge of -3. When this thing dissolves in water, what happens? Remember, they now become hydrated, and the state of matter we usually put for them is that they are aqueous. We say they are aqueous. Now, no matter the type of equation you are writing, whether dissociation or ionic or total formula or net ionic equation, the equation must be balanced. If you look at this, there is 1 potassium here, there is 1 phosphate here. But here we have 3 potassium. What do we do? As usual, we're going to add 3 as a coefficient to balance it, and the equation is balanced. We take that down to the next one. This is ammonium carbonate. Both of these two guys are polyatomic ion. Of course, ammonia is the only polyatomic ion at this level of chemistry we'll talk about. And carbonate is also another polyatomic ion. So what do we do? Now, if this thing breaks down in water, of course, ammonium ammonium will be released. It will be hydrated by water in aqueous solution, and carbonate, on the other hand, will also be released. This is 2 minus aqueous. Now, if you look at the equation, we have 1 carbonate ion here, which is okay, but we have 2 ammonium ion. What do? We're going to add a coefficient in front of ammonium to make the equation balanced. Like I said, any equation you write in chemistry has to be balanced, no matter the type of equation. It has to be balanced because these equations obey the law of conservation of matter. You remember that when we talked about balancing of equation, that the law of conservation of matter is always obeyed. The number of atoms on the left side, on the right-hand side, must equal the number of atoms on the right side. That is the basic understanding. Now again, we have aluminum sulfate here. Let's look at it. Aluminum is in group 3, so of course the charge is going to be 3 plus. Now it's going to be hydrated aqueous. Sulfate, of course, has a charge of 2 minus. It's going to be hydrated again aqueous. Now this is correct because we got the charges of the respective entities in this compound. However, the equation is not balanced. If you look at this, we have 2 atoms of aluminum. So we're going to put what? 2 at this point. And look at sulfate. We have 3 sulfate ions here. What it means is we're going to also put 3 in front of the sulfate, and now the equation is balanced. We go to the next one, potassium nitrate. Again, potassium is in group 1. It's going to have a charge of +1. It's hydrated, we put aqueous. Nitrate, of course, has a charge of -1 aqueous. We look at it, whereas 1 potassium here is balanced, 1 nitrate, 1 nitrate. We do not need to add anything because the equation came balanced easily. So having known to write the dissociation equation of single compounds, how are we going to extend this into when reactions actually occur between 2 compounds? Now, before us to do that, we're going to classify ionic equations into 3 types of ionic equation. The first one is the molecular or formula equation. The molecular or formula equation represents the type of equation whereby each compound is represented by its full formula. You write the full formula of this compound and the state in which it exists completely and balance it. That is what we mean by molecular or formula equation. Now, the total ionic equation will be writing all the equation in ionic form. All substances that are actually dissolved in water have to be represented in ionic form. They have to be ions. Now, some of them can be written not in ionic form, only if they are pure solid, liquid, or gases. What it means is that they will not be dissociated. Now, and then the last one is the net ionic equation. A net ionic equation only represents the unionized or insoluble materials and the ions that undergo those changes. Now, if you write your total ionic equation, we'll find out that some species will occur unchanged on both left and right side of the equation. If you remove those species that changed, what you are left with will be the net ionic equation. And those ones that will be left will only be those of them that are unionized. And of course, those will be pure solid, pure liquid, and gases that are in the unionized form. And those ones that are removed that did not take part in this reaction will be discarded. Those particular ions are what we call the spectator ions. Just like when you're a spectator, you go to watch a football match. The football match is going to proceed, whether you finish watching it or not, whether you even came and honored your ticket or not. So you are a spectator ion. So the spectator ions do not participate in this reaction. They do not participate in reaction. They do not participate in reaction. All right, let's take it off. Well, the best way to understand this is by the time we begin to practice and see examples in what we're doing. So the first problem, the problem 3 here says, write the total formula equation. We're given a total formula equation here. Remember, a total formula equation has all the formulas completely written. It says write the total formula equation below in total ionic. So we're going to put it in total ionic. I represent that with TIE, and net ionic NIE. The total formula equation, I call it the TFE. this is arbitrarily made up by me. Other instructors might use different acronyms, but I try to make my lecture simple and use acronyms so that I don't have to keep writing full words all the time. Of course, as chemist, I'm more conversant in writing formulas and shortcuts. It conveys a lot of meaning to me. So the first thing we need to do is to write what? The first thing is to write the total ionic equation. Now, so the total ionic equation, I'm going to call it like I have the TIE. I'm going to put a hyphen. That's what I want to write first. So what do? I start. I'm going to start breaking everything into ions. Potassium has +1, and there are 2 potassium ions here. So I'm going to just say 2 potassium ions. Now, just to let you know, this equation I gave you already, the total formula equation I gave you is already balanced. So you have to reflect the number of each of these atoms as you are writing these total ionic equations. So this, of course, is in aqueous form. Plus, we're going to break that chloride. Chlorine is in group 7. It's going to be 2 minus. Of course, if you look at this, there is 2. Chlorine is also 2 chloride ion. We're going to have aqueous. This is only representing this. Then the other species, lead nitrate, will start. Plus, lead nitrate. Lead is this here now. You see that nitrate is +1, -1. But because of lead, it has 2 here. So what that simply tells you is that if you have total of 2 minus, lead has to be 2. So this is lead 2 plus. Remember, lead is an extended transition metal. This is aqueous plus our nitrate. Of course, nitrate here has 2. If you look at this 2 is only telling you that there are 2 nitrate ions. So you have to put 2 NO3 minus. Again, aqueous. Yes, aqueous. So what is the next thing? The next thing we do is to put the arrow. Of course, you see, as I'm writing this equation, it's going to spill over. There is nothing bad in it spilling over, so I'm going to finish writing it in the second one. Next time, I'm going to try to see if I'm going to conserve enough space to write all of them. So the next thing I'm going to write now, you see, look at this one. Remember what we said. It is only pure solid, liquid, and gases are unionized. You cannot write them in an ionic form. So this is a solid. It's a precipitate. So we cannot write it in ionic form. So it's going to remain the way it is. So we're going to say this and put solid. And then plus, we're going to finish this one. This one again is aqueous. Therefore, it can be broken into ions. So we have 2 potassium ion aqueous plus 2 nitrate ion aqueous. So this is, I need to put my aqueous. Okay, so probably I'm going to write that so that it's going to give me enough space. So I'm going to say plus 2 nitrate ion aqueous. So this is what I have. Now, if you look closely in this equation now, you're going to be seeing some things commonly. Remember, it said we should write the total ionic equation and net ionic equation. This is the next one. Now, to get the net ionic equation, what we need to do is to strike off things that are called on both sides of the equation. If we use the word, things that appear on both sides, let's use that word. So let's see if there's anything that appeared. If you look at this, of course, we've done the first one. So what we're going to be doing now is the net, I'm going to put it down here, the net ionic equation. If you look at this equation now, what do you see? You find out that, let's see if there are things that appear on both sides that looks exactly the same thing, both in their state and in the formula. So let's see. There is 2 potassium aqueous. There is 2 potassium aqueous here. What this tells you is that, if I'm going to use another color, is that you can cancel out these guys. You can treat this as an algebraic equation that they can cancel out. Let's look at another one. There is 2 chloride ion here. There is 2 here, but this is in a different state. They cannot cancel. This is aqueous. This is solid. They can't cancel. Let's go to another one. There's lead here, lead ion aqueous. Here, lead is existing as a part of a compound in the solid form. It cannot cancel. Let's look at nitrate. There is nitrate ion here, 2 moles of nitrate ion, and there is 2 moles of nitrate ion, and they look alike and in the same state. So this is going to cancel this. These ones that we cancelled are actually what we call the spectator ion. So to write the net ionic equation, now the net ionic equation will be written without these spectator ions, without the ones that we cancelled. So it's going to be net ionic equation will be, let's take away the one we cancelled. If you take away the one we cancelled, what is remaining? We are left with 2 chloride ion aqueous plus lead, 2 plus aqueous will give us what? PbCl2 solid. This is the net ionic equation. Now, those ions that we struck out that were not involved in this last part of the equation, they are what we refer to as the spectator ions. And therefore, the last part said, what are the spectator ions? So the spectator ion, we're going to list them. The spectator ions will be first potassium ion, we struck it out, and the next one will be the nitrate ion that we struck out earlier. So those are the two. So that is how you approach this question. If you want to do, that is how you approach it and solve this kind of problem. Let's go to the next one real quickly. The same thing. It says, write the total formula equation below in total ionic, TIE, and net ionic equation. Again, we're going to start the total ionic equation. I'm going to usually use my TIE, the TIE here. I'm going to start with it. Again, there is 2 sodium ions here. So there are 2 sodium ions. Of course, it's going to be aqueous because this is the state. There is 1 sulfate ion, SO4, 2 minus, aqueous. Plus, if you look at barium here, there's 1 barium. Barium is group 2, 2 plus. Plus, chloride is in group 7, so it's going to be, and there are 2 of them, so it's going to be 2 chloride ion aqueous. And then we go to the other side of the equation. We have listed all the species to the left. Of course, all the species to the left in this kind of reaction, usually in precipitation reaction, will always be aqueous. We go to the right. There must be 1 solid on the right, and the solid was the first given to us. So we're going to write it first. BaSO4 solid plus. Now this is aqueous, therefore this can be broken. So we have 2 sodium ion aqueous plus chloride ion. Of course, this is aqueous. So that chloride ion is aqueous at that point there. So let me try to fit it in. Let's see. So this will be this is plus chloride ion aqueous. Yes. No, that is 2 chloride ion. I messed it up now. It doesn't matter. I can always 2 chloride ion. I'm going to put aqueous here just to let you know. Okay, that's fine. So I don't have enough space. Now the next thing is that I'm going to take off. The next thing is to take off those things that occur on both sides. Let's see. There is sodium here occurring as sodium aqueous. So we're going to take it off. It's a spectator ion. And which one again? Sulfate is not existing as an ion here. Barium is not existing. But we have chloride existing on both sides. We're going to strike it out again. So to write the net ionic equation now, our net ionic equation is going to be sulfate ion 2 minus aqueous plus barium 2 plus aqueous will give us barium sulfate solid. That is the net ionic equation. And the spectator ion is going to be, ions are those of them that I struck out. What are them? Sodium ion, the first, and the other one is the chloride ion. And these are the spectator ion. We go to the next problem. Now, in this problem, now if you look at this reaction, this is an acid-base reaction. We can also write acid-base reaction in both the total ionic equation and the net ionic equation. Of course, remember what I told you when we did the types of chemical reaction is that in acid-base reaction, you must form liquid water as one of the products. That's the most important product. And of course, what that means is that the other part of the equation is going to be composed of the net of the spectator ions. Let's take it off from there. Now, first, the total formula equation, that's what we're writing first. The T, or not the TFE, sorry, the total ionic, T ionic equation. So we're writing first. In writing that first, hydrogen has to break down here. So it's going to be 2H plus aqueous plus, there is chlorine is 2 and it's -1 aqueous plus magnesium is in group 2, is going to be +2 charge, and we only have one of it there, aqueous plus, now OH group is a single entity, it's an anion, so it's going to be OH. Now there are two of them. If you look at that, it has a parenthesis, tells you that it's more than 1 mole. So 2 moles of that is going to be plus 2 OH minus aqueous, and then we have our arrow. The arrow will be pointing. If you look at these two, this is aqueous as well. It tells you that it's going to be broken down in water. So it's going to be aqueous plus, there are 2 chlorine ions here, so I'm going to say 2Cl minus aqueous plus. Now what do you have there? You found this is a liquid. It's a pure liquid. It's not going to be broken down. So we're going to leave it exactly the way it is. So it's going to be 2H2O liquid. That's what we have in there, 2H2O liquid. Trying to fit that in there. I think I have enough space to fit it in. 2H2O liquid. Yeah, that is what I have there in that reaction. So let's now see which one is the spectator ion. I'm going to use my green again. Hydrogen ion is not occurring in another place here. It cannot be. Let's see, chloride ion aqueous, and there are 2. Most of them is going to cancel. What about magnesium? Magnesium on this side aqueous, magnesium here is going to cancel. OH is not appearing in another place here, so it's not going to cancel. So if we're going to write, of course, the net ionic equation, what are we going to have? Then we've removed this one, so we're going to come in with hydrogen, 2 hydrogen ion, which is aqueous form on this side, plus 2 OH ion, aqueous on this side, to give us 2H2O. And if you look at it, the equation is balanced, because here hydrogen is 2 plus 2 is 4, 2 times 2, 4. Oxygen is 2, oxygen is 2, the equation is balanced. And what it means is that the spectator ions will be, what are the 2 things we cancelled? First one is chloride ion and magnesium ion are the spectator ions. Now, the next one, this is a single replacement reaction. We can also write it in total ionic and the net ionic equation. So what is happening here? Let's see what's going on here. Again, remember, solids cannot be written. Pure atoms that exist as solid, liquid, and gas, whether atoms or compounds, cannot be broken down. So we start from this one. In writing the total ionic equation, this is aluminum solid, so we're going to leave it there. It's not going to break down. Plus, this is aqueous. What it tells you that this is going to break down. And there are, because this equation is balanced, there are 3 moles of zinc, so we're going to write it 3Zn aqueous plus sulfate. There's also 3 sulfate ion here. That's what it means. These 3 will affect both of these 2. Remember here, zinc has 2 plus because sulfate is 2 minus. And of course, zinc is a transition metal, but it's one of those transition metals that have a constant charge. So what it means is that sulfate, of course, is always SO4 2 minus. So we're going to, and there are 3 of them. So we're going to say 3SO4 2 minus aqueous. And then we got everything on the reactant. On this side, we now have another aqueous here. It's going to break apart, and this is aluminum. What it means is that aluminum has 2 what? 2 moles. So 2 atoms. It's going to be 2Al. Aluminum is in group 3. It's going to have a charge of +3, and it's aqueous. Plus sulfate again is appearing here, and sulfate here is 3. So it's going to be SO4 3 minus aqueous. I didn't put the 3, so I'm going to create a space for myself for that. You have to always put the number of species there. So this is 3SO4 2 minus aqueous. Then plus 3Zn solid. Good. This is what we have in the equation as the total ionic equation. So what of the net ionic equation? Let's see if anything can cancel. That's the next thing we do. Let's look at it. We have aluminum solid, aluminum aqueous. It cannot cancel. You cannot cancel an aluminum solid with aqueous aluminum. That's not possible because aqueous aluminum means you have a compound there that is different. Here zinc is solid. Zinc is aqueous here. Zinc is solid. It cannot cancel. Let's look at the sulfate is aqueous, 3 moles. Sulfate is aqueous. This is the only guy that will cancel around here. So for us to write the net ionic equation, NIE, that will give me 2 aluminum solid, 2 moles plus 3 moles of zinc aqueous will give us 2 aluminum 3 plus aqueous plus 3 Zn solid. And then the only spectator ion here is 1, will be sulfate 2 minus. That is the only spectator ion at these points. Now, always feel free to pause this video, try some of these problems, and always come back to this and test yourself for understanding and comprehension. Let's now go to solubility rules. Now, solubility rules, or some people might refer to it as solubility table. This, of course, is a table. Shows the solubility of common ionic compounds in water. What is their behavior in water? They break when they have in water. Now, the way I made this table, the best thing the students need to do, I made it very clear that students will quickly go and see the exceptions from the general rule. So let's take some examples. Now, it's usually soluble. The first groups are usually soluble. These ones are the exceptions. The exceptions are usually where you have to know what will form the solids forms at this point. The solid we're looking for. So all group 1 elements, including ammonia and nitrate, are all soluble. It tells you that the remarks is there. So all these guys are all soluble. Nitrate, all nitrate are soluble. Acetate, all acetate are soluble. So anywhere you see these 3 guys, any salt they contain, no matter the group of what the metal is, if you see them, if you see acetate anywhere or nitrate anywhere, that salt has to be soluble. Now let's go to chloride, the bromide, and the iodide. If you look at that, if you get to this side, it begins to tell you that all common chloride, bromide, and iodide are soluble, except it gives you the exception. So what it means, if you see reactions involving a chloride and you see silver chloride, mercury chloride, mercury 1 chloride, lead 2 chloride, silver bromide, mercury 1 bromide, lead 2 bromide, and all these guys listed, you now know that this will form insoluble salt. Again, we go to this one, the sulfate. You see, the sulfates are all soluble, except calcium sulfate, strontium sulfate, and lead 2 sulfate. Whenever you see them, they are formed. Now, the ones that form precipitate, usually very insoluble at all, are the phosphate, the carbonate, and hydrogen. These guys are soluble except if they form with the group 1 element, which is the lithium, sodium, potassium, rubidium, cesium, or ammonium ions. Every other one here from phosphate, carbonate are all insoluble. Now, the hydroxide are also insoluble. The exceptions to the solubility are those ones that dissolve a little bit, are the calcium hydroxide, strontium hydroxide, and the barium hydroxide. Again, sulfite are usually insoluble. Another good exception will be the ammonium, those of them in group 1, calcium sulfide, magnesium sulfide, strontium sulfide, and barium sulfide are the exception. So we're going to try to do some problems and try to apply this in using it to predict. The importance of this is to use it to predict both the product of the reaction with the knowledge of our reaction, and then the state, whether it is solid or aqueous of the product. So we're going to start out with some of these problems now. It says, predict the product of the reaction using the solubility table, and then provide the balanced formula equation. So you're going to complete it and provide this equation. You now make it total ionic and make it net ionic. So that's what we're going to do. So first of all, remember when we did this earlier. Remember when I did this earlier, I told you if you're going to write this type of reaction, I'm going to create a small space here. The first thing you need to do is to predict the product, is to know what you have in there. So let me just break them apart. Potassium is in group 1. The first one is going to break potassium and carbonate. Carbonate is 2 minus. You have to memorize this by now. And then now the second one is calcium. Calcium is in group 2, 2 plus. And nitrate. Nitrate is NO3 minus. In precipitation reaction, what happens? They will swap their partners. If I use my green, this guy will go and make this one. This guy will go and make this one. What they simply do is to exchange their charges. So if we exchange their charges, the first one, calcium will be with this one. This is 2 plus. This is 2 minus. So it's just going to be equal. What do you have? You have your calcium carbonate. Don't put the state yet. Let's say plus. And then potassium and nitrate is minus 1 plus 1. Again, it's going to just give you don't need to put anything in parentheses or put anything as a subscript because the charges are equal. Now, you've written correctly what the product looks like, the identity. Although the equation is not balanced yet, and you don't know how do we know the state? We don't know the state. We don't know the one that will form a solid. What do? You go back to the solubility table. Now, the two things you have there are the nitrate. Remember, if you already memorized it, you said the nitrates are all soluble. So if I were you, I'll just put this aqueous immediately. But let's just go look at that table. First of all, there's nitrate. All nitrates are soluble, no matter what the cation is. So you can easily put it. Again, let's look at the carbonate. They're usually insoluble. All carbonates are insoluble except group 1 and ammonia. And calcium is not group 1, of course. Calcium is not group 1, it's group 2, so it will be insoluble. So this becomes, from that note, this becomes our solid and this becomes our aqueous. Now, we've been able to situate our what? We've been able to situate our state. Now, what next are we going to do? We're going to balance the equation. So this is the first thing. This is actually what we call the total formula equation, TFE. This is actually the total formula equation. That's what we have here. Now we're going to be writing the total ionic equation, but before we do that, we have to balance this equation. What do? I'm not going to be using table. We've used table in the previous classes. You can always review that and come back and try your balance. There is 2 potassium here. I'm going to put 2 here. Now my potassium is 2, but look at my nitrate. My nitrate is messed up. It's now what? 2. If I go back to fix my nitrate, luckily enough, it is 2 already. My carbonate is 1, my carbonate is 1, my calcium is 1. So nothing to do again. We'll just add 1 here, add 1 here, and add 1 here. And the equation is balanced. If that equation is balanced, now we have to now go and write the total ionic equation. Again, the total ionic equation will be written by breaking everything into ions, except the solid. So let's start. Here is going to be total ionic equation. Here there are 2 potassium ions. It's going to be in aqueous. Plus CO3 is 2 minus. It's going to be aqueous. Plus calcium is in group 2, aqueous. Plus there are 2 nitrates. So we're going to say 2NO3 minus aqueous. So everything on the left has been represented. We'll now go to the right. Remember, to the right, this is a solid. We cannot break it, so we have to write it the way it is. Plus, now this is aqueous. It has to be broken apart into ions. So here we're going to have, again, 2 potassium ion, which is aqueous, plus there is 2 nitrate as well, 2NO3 ion, again, which is aqueous. So we've gotten our TIE, total ionic equation. So what we'll be left with is our net ionic equation, and then we're going to talk about the spectator ions. But before we do that, I use my green again. Let's see what appeared on both sides. Potassium and potassium are called on both sides aqueous. I'm going to take it out. Let's look at carbonate. Did not. Carbonate forms part of the solid. Cannot. Calcium forms part of it. Not. Nitrate is going to be cancelled. And then, if we'll now write the net ionic equation will be. The net ionic equation will be these ones that are not cancelled. So which will be CO3, 2 minus is aqueous, plus Ca2 plus aqueous. That will give us CaCO3 solid. And this, okay, wait, I'm going to write this thing very well. And that is the net ionic equation. Now, what are the spectator ions? Those ones that I cancelled out. Spectator ions are those ones that I cancelled out. Potassium ion and nitrate ion. Now, feel free to pause this video to try other problems I have coming up. And then when you try them, you can always come back and check for comprehension. This is exactly the kind of question we did again. Another precipitation reaction. So that is what we have here again. Let's take it off again. So I usually try to draw my small box here to help you figure out the product. Again, rubidium is in group 1, Ruby. So you know it's going to be 1 plus. Phosphate is what? Usually PO4, 3 minus. Now, for the second one, barium is in group 2, is going to be Ba2 plus. And then chloride is in group 1, is going to be 1 minus. So what do? We now do what? We exchange the radicals. We exchange their charges. So what do? They swap their partners and exchange charges. So we do that. So we now begin to write them. So it's going to be rubidium is in group 1, is joining this guy, of course. What is it going to be? Okay, I'm going to write this one first. I want to write this. So this will go to this. Remember, barium, let me use green. Here, barium is 2 plus. Here is 3 minus. If they exchange, if they swap those charges, barium is going to get the 3 from phosphate, and phosphate is going to get the 2 from barium. And because it's a polyatomic ion, you have to put parentheses, and this is going to give you this. Plus. Now, rubidium is in group 1, Ruby. Chloride is in group 7. The charges are 1 to 1. So what you need to do is to bring it down. So this is going to be Ruby, Cl. No, we don't know the state yet. I don't want to preempt it. Now, what do? We have to know what the state are by looking at our table again. I know what it is already, but let's go to the table and look at it. Let's go to the table. If you go to this table, now look at usually insoluble. If you look at the usually insoluble, what do you have there? The phosphate. Do you have, so all phosphates are insoluble except ammonium and group 1. If you look at that one, there is no ammonium here. There's no group 1 here. Therefore, this is going to be our solid, and this is going to be our aqueous, because all chlorides are soluble except a few of them that were listed. So we got our state. Now, the next thing will be you have to balance the equation. That is the next step. In trying to balance this equation, let's see what we have here. Now, let's start from balancing from metals first. Here, barium is 3. Barium is what here? 1. So I'm going to put 3 here. If we put 3 here, chloride now becomes what? 6. I have to fix my chloride. So to fix my chloride, I'm going to put 6 here. My chloride is fixed. However, my rubidium has been messed up. I'm going to fix it. To fix it, 6 here, I'm going to put 2 here. It is now correct. And then, and it appears the equation is balanced. Let's check everything. 6 rubidium, correct. We have 2 phosphate here. If you look at this place, there are 2 phosphate coincidentally balanced. 3 barium, there is 3 barium here balanced. 3 times 2, 6 chlorine, and there is 6 chlorine atoms here, and the equation is balanced. So our total formula equation has been written correctly, the state written and balanced. And now what next we do? We want to figure out the total ionic equation. The total ionic equation is TIE. What is our TIE? Again, on the left side, all aqueous, they're going to be broken down. So how many? This is 6. Of course, this 2 times 3 is 6 ROB ion aqueous plus. Here, phosphate is 2. 2 times 2 is 2 phosphate. So you're going to say 2 PO4 3 minus aqueous plus. Barium here is, of course, barium is, we already said it's 2 plus, but here it's 3. So we're going to say 3 barium 2 plus aqueous plus. Now, how many chlorine do we have here? 3 times 2, 6 chloride ions. So it's going to be 6 Cl minus. This will give you aqueous. Now we've gotten everything situated on the left side. What about on the right side? Let's move. Remember again, the solids, the pure solid, liquid, and gases cannot be written in ionic form. So we're going to bring down our barium phosphate, Ba3, PO4 bracket 2 solid, plus our rubidium chloride. Of course, this is aqueous again, and there are 6 rubidium ions, so we're going to say 6 ROB plus. Again, this is aqueous plus. Chloride is also 6 chloride minus. Again, this is aqueous. Now, we've been able to situate all of them. The next thing we do, this is our total, is to write our net ionic equation. To write the net ionic equation, I usually tell students, the first thing you want to strike out your spectator ions. Let's see those of them that are called. So what it means, anything that is not barium and phosphate is going to cancel. So there's rubidium here, it's going to cancel rubidium on the other side. The same thing, the same state. And then phosphate can go, barium can go, chloride is looking exactly the same, we're going to take it off. So our net ionic equation is going to be 2PO4 3 minus aqueous plus 3Ba2 plus aqueous to give us the solid Ba3PO4 bracket 2 solid. So this, and if you look at it, there's 2 phosphate ions here. We have it. There's 3 barium atoms, and the equation is balanced. And now, what will be my spectator ion? Spectator ion. My spectator ions is going to be the ones I cancel out, which is rubidium ion and which one again? The chloride ion. At times, what students do is that they begin to write, okay, 6 barium ion, as it doesn't matter. What we want here in spectator ion is to identify, just to know what they are, just to list exactly what they are. All right, so we're done with this one now. Successfully done with it. We go to the next one, problem 9. You can always pause this video, try this yourself, and come back and see how that goes. Remember, most of my slides, I tell you, most of my lectures, we solve a lot of problems so that you're going to get conversant with these problems as you watch the videos. Now, again, we have something familiar. Remember, we talked about ammonium ion. Anything with ammonium ion will always be soluble. Remember, let's see. Okay, let's move. Again, I'm going to draw myself a small box here where I'm going to situate it. Ammonium ion is just the only positive polyatomic ion you're going to know for now. So this is NH plus is 1 plus, OH minus is 1 minus. Then ion, if you look at that, sulfurate is 2 minus. For it to balance ion, this ion has to be 2. So this ion 2 plus, and sulfurate is SO4 2 minus. That's exactly what we have over there. Now we're going to use my green to swap. If these guys swap, exchange their partners and then swap their charges, what is it going to be? First of all, you see ion is going to this, so this to this. Now this is -1, this is +1. So what that means is that if they swap it, ion is going to take the 1. We don't have to write it. And then OH is going to take the 2 of ion. And then, oh, we don't write the state yet. Plus, what else? Now, ammonium and sulfate is going to come. They're going to become partners. You see, ammonium is 1 plus. This is 2 minus. If they exchange, what it means is ammonium is going to get 2. And because it's a polyatomic ion, you have to put a parenthesis. And then sulfate to take the 1. This will now be the formula. So, if ammonium hydroxide reacts with iron 2 sulfate, you're going to form iron 2 hydroxide and ammonium sulfate. We don't know the state. Now, we have to use the what? We have to use our solubility table. If you go to the solubility table again, let's look at it. It's usually insoluble with the hydroxide. See the hydroxide, all hydroxides are insoluble except those of them with ammonia and group 1, and calcium hydroxide and strontium and none of them is there. So what it means is that the hydroxide there is going to be solid. So we're going to put it, this will be our solid. And then, of course, anything involving ammonium ion is going to be the aqueous. So this is our total formula equation written. Now, we've not balanced it. To balance this equation, let's see. Now, let's look at ions. Let's look at the metals. this ion is 1, ion is 1. That is okay. We don't have problem with that. Let's see balanced polyatomic ions then, the next. Here hydroxide is 2, hydroxide is 1, so I can add 2 here. I have to, but I've messed up my what? Ammonium. Fortunately, my ammonium here is 2, so that makes it good. And what it means is that the equation is balanced at this point. So even if you wanna, the equation is balanced. So even if you wanna add 1 to this side, that's fine. You can usually add 1 here, add 1 here. The equation is balanced. So what do we do next? What we do next is to write the net ionic equation. So the net ionic equation, of course, is going to be, we'll break everything into ions. We have it here already in this small scratch box. So it's going to be ammonium is 1 plus, and here there are 2 ions. So we have to specify that. So it's going to be 2 ammonium ions aqueous plus hydroxide ion is also 2, so it's 2OH minus aqueous plus here ion is 1, 2 plus aqueous plus sulfate here is 1 minus aqueous, 2 minus aqueous. And then the next thing we do is to go to the other side. If you go to the other side, ion 2 hydroxide here is a solid, so it cannot be broken. So we're going to just write it down. FeOH bracket 2 solid plus. We're going to write the other one. Now, if you look at this, this is aqueous. What that simply means is going to break down. So we're going to have 2 ammonium ion here, aqueous, plus sulfate ion, SO4, 2 minus aqueous. So this is our net, this is not our net, this is our total ionic equation. I actually made a mistake here. This is the total ionic equation. TIE. Now, what about the net ionic equation? My net ionic equation will be, first of all, let me strike out my spectator ion. Let's look at it. Aqueous ammonium is 2 moles and existing on both sides here, the same thing. We look at sulfate existing on both sides and the same thing. So having struck them off, I'm going to write my net ionic equation. So this is going to be 2OH minus aqueous plus ion Fe 2 plus aqueous. That will give us the solid. The solid is FeOH bracket 2 solid. This is the net ionic equation. And then what are the spectator ions? The spectator ions are those guys that we just struck. So the spectator ions, those ones we just struck out. And what are they? They are ammonium ion and sulfate ion. Those are the ones that we just struck out there, and they are the spectator ion. The next problem. If you look at the next problem, this problem is actually a single replacement reaction. Remember when we did it first time, when I gave you the total formula equation and we're writing the total ionic and net ionic, we had a problem like this. So what do we do? Let's see. Again, remember, lead is existing as a solid, cannot be written. So what you need to do, I'm going to get this box again, this scratch box that helps us. This scratch box is very important, helping us. So we're going to have lead alone here. It doesn't have a partner, so you're going to leave dash there. And then here we have silver nitrate. So silver is 1 plus. It's a transition metal, but it has only 1 charge. And then NO3 minus. Now what is it going to do? They're going to swap their partners. So look at what's happening here. Lead will go and make this one. That's what lead is going to do. But silver doesn't have anyone to go to. So silver is just going to go and be alone as Ag solid. That's what is going to happen to it. So if we do that, what do? We now go back and finish it up. So if lead goes to this guy, lead is 2 plus, of course. Now, lead is going to be 2 plus because the commonly existing one is usually 2 plus. So we're going to make this lead 2 mainly. So what is that going to be? So lead is going to go join this guy. So it's going to be lead is 2 plus. So, and this is lead 2 plus. This is 1 minus. Lead is usually 2 plus. So lead is going to get to this. Take 1 from here, you put 1, but you don't need to show it. And nitrate will take the what? Nitrate is going to take the 2. And plus the silver. The silver have nobody to meet. Because it doesn't have anybody to meet, it's just going to form an atomic solid, a pure silver atom. Now, one of these guys is going to form the solid. Now, let me give you a secret. Anytime you see an atom written on its own, it is usually the solid. Because an atom will not exist on its own as a charged something. It has to exist on its own as neutral atom. And a neutral atom is not charged. It's usually a solid. So, that's exactly what we're going to be having here. So, and therefore, but if you look at the solubility table again, it says all nitrates are soluble. Therefore, this is going to be the aqueous. And now we're going to balance it. Lead is 1, lead is 1. Silver is 1, silver, but nitrate is 2. So what they're going to do, just add 2 here. Nitrate is 2, but my silver is messed up, and I add 2 here. The equation is balanced. You cannot add 1 and 1. So this is our total formula equation. Predicting the product and balancing it. Then what will be the total ionic equation? The total ionic equation here will be, we start writing. Remember, this cannot break down. It's going to remain solid. Plus, this can break. This is aqueous. So this is going to be Ag1 plus aqueous plus, of course, it's 2 ions. So we're going to put 2 here. And then plus, what about nitrate? Nitrate is 2 moles 2. So we're going to put 2 NO3 minus aqueous. Now, this is going to go to, this one becomes the aqueous again. So therefore, this is Pb, 2 plus, will give you aqueous, plus nitrate is going to give you aqueous. Again, nitrate here is 2. And then silver here is going to give you solid. Again, plus 2Ag solid. This becomes the total ionic equation. You see that we wrote everything in ionic equation except those of them occurring as solid. Now, so if we're going to remove our spectator ion, something that appears on the same side that looks the same thing. Here, lead is solid, it is ion, here is not. We're going to take it away. Silver is ion, here aqueous, here is solid, we can't take it away. Nitrate is aqueous here, and ion and aqueous, ionic, so we're going to take it away. And then what it means is that my net ionic equation is just going to be lead solid plus 2Ag plus aqueous will form Pb 2 plus aqueous plus 2Ag solid. And if you look at the equation is balanced. Equation is very balanced. And of course, the spectator ion, just one of them, and that's going to be what? The nitrate ion. Now, you can always pause this video and then always come back and then try this yourself and check your answer. The last but not the least we're going to do here is acid-base reaction. Again, acid-base reaction can be written in both total ionic and net ionic form, and we can easily isolate. Now, remember what I told you. In every acid-base reaction, water molecule has to be formed. In the pure water, it has to be a liquid. So usually that's a shortcut to get it. So let's see what happens here. But I'm going to do this again. Now here, hydrogen is 1 plus ion in every acid, and phosphate is 3 minus. Here, potassium is group 1, 1 plus, OH is 1 minus. If these guys trade, exchange, or swap their partners, what's going to form? Now, hydrogen is going to go to this one. Whenever you have one H and OH, it's going to form, remember what we said? It's going to form water. That's what it's going to form. It's going to form H2O. So it's going to form H2O. Of course, it's going to be a liquid. I'm going to put it now plus. Now, again, I told you, in acid-base reaction, we did it when we did types of reaction. The two things form, they don't form solid. Everything is aqueous, dissolved in water. So plus, now we're going to see that potassium and this. We're going to see that. So if potassium interacts with this, potassium is 1 plus, phosphate is 1 minus. They're going to exchange their charges. So potassium is going to take the 3 here. So it's going to be K3 and PO4 1. Since it's one ion, we don't have to put parentheses. So this will be the product of this reaction. However, we are not done because we need to, I told you, every equation has to be balanced. You have to write the balanced chemical equation no matter what type of equation you are writing. So that is what we're going to be doing next. Now let's try to balance the equation. Let's see. Now, I usually like starting with the ions. It pays a lot to do that. We have 1 potassium ion, 3 potassium ions here. Starting with the metals helps a lot. So this is 3 potassium. Now, what have I done here? Now, if you look at what I've done here is that I've messed up my OH ion. But if you look at it, I don't have OH on this side, so I don't need to bother about that. So I'm going to see it as what? Oxygen and hydrogen. But before we do that, let's balance another polyatomic ion we have here. Let's see. There's 1 phosphate here, there's 1 phosphate, so we're done. Basically, what we need to balance is the number of oxygen and hydrogen with this water. That's what we need to deal with. So what do we do? Now, let's count. There is 3 hydrogen plus 3 hydrogen here, which is 6. And this is only 2. If you add 3 here, this becomes 3 times 2, 6 hydrogens to the right. Now, that happens to our oxygen. Our oxygen now becomes 3 here. Fortunately, our oxygen is 3 here already. So the equation is now balanced. You can always add 1 to the other ones that do not have any coefficient in their balance. Now, let's write the total ionic equation. We'll start breaking everything down. We've done that already in the scratch box. So, but we'll just write it out. So the total ionic equation will be, again, this will break into, there are 3 ions. This 3H plus, aqueous, plus phosphate is only 1, PO4, 3 minus, this is aqueous, plus, there is 3 potassium ion here, so we're going to say 3K plus aqueous plus 3OH minus, because there are 3 hydroxide ion. What does it form? Remember, pure solid, liquid, and gases cannot be written in ionic form. This is water molecule, so we're just going to write 3H2O liquid. And then the next thing, plus. Again, remember what I said, I didn't finish this. In acid-base reaction, you don't have any solid, so you only have the water and the aqueous unit. And of course, since you have potassium here, you can use the table to predict all metals that have, all salts that have group 1 element is always soluble. So potassium is in group 1. So if, assuming you want to still use the table, but in this case, in acid-base reaction, you do not have to use the table to do that. Now, what next do? We go to the next one. So this is going to break apart. So this is 3 potassium ion aqueous plus 1 phosphate. The phosphate is PO4, 3 minus aqueous. So this is the total ionic equation. Now, to figure out our net ionic equation, we're going to cancel out what we have on both sides that didn't change. Let's start. We have hydrogen ion here. We don't have anyone here. We have phosphate ion here, aqueous. We have phosphate ion here. We're going to take it away. We have 3 potassium ion here. We have 3 potassium ion aqueous in the same state. We take it away. And we don't have any other stuff again. So if I want to write my net ionic equation, so the net ionic equation is going to be my 3 hydrogen ion here, aqueous, plus 3 OH minus aqueous to give me 3H2O. And when you count it, you find out that the reaction is balanced. Let's count. 3 plus 3 hydrogen, 6, 3 times 2, 6, 3 oxygen, the equation is balanced. Again, I said, no matter what type of acid or base that react, the net ionic equation is constant. It is the formation of water that will form in the net ionic equation of any acid-base reaction. And then what will be our spectator ion? Our spectator ions will now be those ones we struck off. What are they? Here we have the phosphate ion and which one again? The potassium ion. You do not need to write their the number of atoms there existing on the moles, because we just want to identify what they are and not how many in there. It has been a long ride in this lecture. Thank you for listening, and have a wonderful day ahead of you. Bye.